going to put this in our notebook so that you can use it on your tests. And we're going to review geometric sequence. We hit this at the beginning of the year a little bit, but it was Chapter 6, which we skipped. Chapter 6 is called Sequences and Series, and for those of you that are going on to Pre-Calc, you're going to want to make sure that you go back and spend some time on Chapter 6. You can get into it through Mathia. You can also take a look at the topics in our textbooks. But geometric sequence is a sequence where the terms are generated by multiplication. And what we multiply by every time is called our common ratio. And we call that our R value. So in our formula, the common ratio is going to be our R value. So here's an example. So we look at what are we multiplying by each time here. So our R value here is 2 because we're doubling. So we've got a couple different ways to express a sequence. The first is what's called the explicit formula for a geometric sequence. And this is the notation. So second hour saw this before, 7th hour, this is new to you guys. So G sub n just stands for the nth term of a geometric sequence. So if I said G sub 50, that would represent the 50th term. G sub 1 stands for the first term. R is our common ratio. And up here, the exponent, n, is the term number. So if you're talking about the 50th term, n would be 50. Okay, so one thing you want to keep in mind in Chapter 1, a lot of you had trouble when you saw something like this, a geometric sequence that was dividing by 2. Many people wanted to say the common ratio was dividing by 2. The common ratio always has to be expressed as what you're multiplying by. So dividing by 2 is the same as multiplying by a half. So in this case, our R value would be 1/2. It's getting half as big every time. So always think about it in terms of multiplying. Okay, so then we go over here and we want to start kind of generating some terms. So up here, our first term is 1.5. So let's go over here, go to first term, 1.5. Okay, so we just plotted when n was 1, our first term was 1.5. So then we go out here when n is 2, we go up to 3. When n is 3, we go up to 6. And when n is 4, it goes way up here to 12. So if you have to pause the video to kind of keep up, go ahead and do that. But notice that if we start to sketch this, we can see that exponential growth happening. That it's definitely not linear. It's growing exponentially. So our formula for this example up here would be our first term is 1.5. So we put that right out front. Then we multiply by our growth factor of 2 to the n minus 1 power. Okay. Notice that this does not generate the 0th term. And so therefore, if we wanted to look at this as a function, we wouldn't be able to see the 0th term would be the y-intercept. So to figure out that 0th term, what would we have to do? Any ideas? If we're doubling to move to the right, if we have to find the 0th term, aren't we moving back here 1? So we would have to divide by 2. So what is 1.5 divided by 2? 0.75. So we can plot that right here. We can see that we have a y-intercept of 0, 0.75. Okay. So we want to turn this sequence and the explicit formula, we want to write it in function form. So function form of an exponential looks like this, where A is our y-intercept and B is our common ratio. Oops, ratio. So if we put this same equation, this same scenario into function notation, we wouldn't start with 1.5. Now our very first number is going to be what our y-intercept is. So that's going to be 0.75. Is our growth factor still the same? Yep. So that will be 2. But now it's just to the nth power. Okay, so I want to take just a minute to see the difference. Here, when we start at 0.75, to get to the third term, which is up here, 1, 2, 3, to get to our third term, if we started at 0.75, wouldn't we have to double it 1, 2, 3 times? So in function form, the exponent matches whatever term you want. If you want the third term of the sequence, you're going to multiply by 2 3 times because you backed it up 1 and you started 1 behind. Okay. All right, so let's go down here. We're going to write each of these sequences in function form. So looking at this scenario, do you see that our starting value is 0.5 and our growth factor is 1.25? So for function form, we don't need our starting value. We have to back it up 1 and we have to find the y-intercept. So can you please divide 0.5 by 1.25? And somebody tell me what you get. 0.4? Okay, so that's going to be 0.4 is our y-intercept. We still have our growth factor of 1.25 to the nth power. Okay, now Joey, can you calculate this when n is 2? Sam, can you calculate it when n is 3? And can somebody else calculate it when n is 1? And give me those numbers when you've got it. N is 2. 0.625. Okay, what'd you get for n is 1? 0.5. Okay, did anybody get it for n is 3? Okay, we need to go farther. Can somebody do it when n is 6? Okay, so that's still not, I don't like how this is going, so I'm going to change these. Okay, can somebody do when n is 10? Three-point what? Okay, so this one grows slower, but you can start to see that it's starting to make an exponential pattern. Okay? Okay, so let's go to this one. What is the first term of this sequence? 150. And the growth factor is what? 0.8. So it's going to be getting smaller. So we're multiplying by 0.8. So to go backwards, we have to divide by 0.8. So can somebody take 150 and divide it by 0.8? 187.5 is our y-intercept. So here it's in function form. And because we're running out of time, please change your y-axis. Sit down, please, to these. That means it's going to hit up here at 187.5. And I need some people to put in some numbers here. So somebody do 4, 6, 8, and 10. and tell me what you get. Somebody put in for 4, someone else 6, 8, and 10. 4 is 76. Okay, can somebody do 2? 8 was 31. Okay, can someone do 2? It does, because look at, it's going to be decreasing like this, exponential. Okay?